And now we are happy to announce the next speaker from RWTH Aachen University, Camila Oprea. There she is. Yes, with her talk on explainable AI in the analysis of medical time series. And here we have it.
Yeah, sorry. No problem. Good luck. Thank you. Yeah, thank you for the nice introduction. I also sadly couldn't pull off the nice dark slides, so I'm sorry for the boring white slides. But for the title, I did use this one. So before I jump to Explainable AI, I would shortly like to motivate the ever-increasing interest in medical time series. And I can do that with a nice example of intensive care units and the data that is collected there through the continuous digital transformation and the ever-growing and changing infrastructure that we have in intensive care units. So on the right side, you see the setup that we have in our neonatal intensive care unit in Aachen, where on the right side covered is the incubator, and around it you have a multitude of monitors and that show different sensor data that we can record. So we have monitoring and therapy ICU data, and we're also lucky enough to have set up an infrastructure to record all this high-resolution data, which gives us a high-resolution polygraphic data collection. What does it look like? I've gotten here an extract of 12-hour recording of intensive care data, where we have from top to bottom pressure during ventilation, flow and volume, and on the bottom oxygen saturation. So what can we do with it? We can detect trends, we can detect outliers, we can also detect complications, for instance, a serious drop in oxygen saturation. But this is over 12 hours, so this is easily done manually. But what if we zoom in and we look at 20 seconds? Now we can see the individual breaths that you can discover every time the pressure rises. And here also we can detect breath-wise complications. But this 20-second recording has a multitude of breaths. This is not easily done manually anymore. So this is not feasible, neither for healthcare professionals nor for other people. So this is where AI steps in. And this is how we can leverage the multitude of data that we have. And there are different strategies to cope with time series because they do have this temporal aspect to them. So it's more difficult to analyze them. For instance, we can use distance-based algorithms where we compare the distances between two sequences and see which are most alike. We can look for certain shapes that hint towards a complication, or we can use more difficult features which are computed by neural networks. So here we have a temporal convolution neural network, but that's not that interesting. What is more interesting in this talk is, do we understand what these algorithms do? I would hypothesize that in the first two, we could. So distances is something that we get. Shapes is something that we can understand. But neural networks, it's more difficult for us. All the numbers, all the weights in the neural network, and all the parameters that are adapted is not that easily for us to understand. There's also the usually made assumption that there is a trade-off between explainability of an algorithm, how well we understand it, and the performance. So for instance, a decision tree, which is more explainable, but might not be able to grasp difficult concepts, such as a neural network. So the question arises, if more explainable algorithms might have less performance, why are we even interested in explainability? And for that, I would try to do a small interaction with you. And I have brought 4 scenarios. And the question in each scenario is, do you want additional explanation to the answer of an algorithm? And I did use this to use a plethora of images I have of my cat and dog to ask you, in the scenario of a classifier that just differentiates between a cat and a dog, would you want additional information on why it is a cat or why it is a dog? Maybe just show your hand up if you want additional information. Okay. So we have a few hands, a few curious people on how the classifier is working. Now let's go back to our time series. If we have single breaths and I want to detect if a breath is normal or not, and the decision is normal or not, do you want, in that case, additional information? Okay, so a few more hands. Yes, that was to be expected. Now we look at oxygen saturation, and I have a predictor who will tell me that the oxygen saturation will stay okay or not, maybe over multiple hours. What about this time? Do you still want an explanation? Okay, about almost at the same time. Same amount of hands. So for the last example, let's consider pneumothorax. The classifier takes X-ray scans and has to tell me if there's a pneumothorax there, yes or no. Do you now want an explanation if additional to the answer yes or no? Okay, I see nicking, I see, this is obvious, right? Of course, so it's depending on the gravity of the situation, how high risk this is. And it's not only our opinion and your opinion, if we need an explanation or not, it's also the opinion of the European Artificial Intelligence Act. According to Article 6 of which, we can classify medical systems as high-risk AI systems. And then Article 13 has to hold, which states that systems should be designed and developed to ensure that operation is sufficiently transparent to enable deployers to interpret the system's output and use it appropriately. Now, there are multiple articles, but I don't want to bore you with that. So it's not only our opinion, but there is also necessity to provide for sufficiently transparency. There's also different questions that come up in the research community applying AI in medical fields, also the ethics part of it. Can I trust the AI? Can I, as a patient, can I, as a healthcare professional, trust it? What about bias? Data is inherently bias prone, so what about the algorithms that are based on it? And lastly, also, who's responsible in case of a hazardous event? Do we blame the healthcare professionals or maybe the developers who implemented the algorithm? And this is the field that Explainable AI tries to cover, where we try to understand the inner workings of an algorithm, or even provide mere human understandable insight into the outcome of one single classification. So basically, our idea is to open up this black box and make it into a white box. Of course, with this wishful thinking, we usually land somewhere in between with a gray box. And the question is also how? What methods do we use? What is best suited? And before I go into the methods, I would also want to ask the question, for whom do we do this? Who are the stakeholders that this explainability to provide any additional informations? And when applying explainability, there are four main stakeholders. We can look at the consumers, for instance, the patients that are in therapy. We can look at the users, for instance, healthcare professionals who are employing these AI high-risk systems, but also the businesses who deploy them and develop them. And lastly, as we've already seen, the regulators and also the lawmakers. Okay, so we have in mind what we want, who we have to consider in this process, and now to three very simple XAI methods, just to give you an insight how this can work. We have LIME, SHAP, and Grad-CAM. And LIME and SHAP both work in a similar way, where they try to change the input features of an algorithm and see what effect that has on the outcome. And for instance, we can change the values and see in which direction the outcome sways, or we can omit a value or a feature and see how then the outcome changes. Grad-CAM works best, for instance, on image-based classifications, where it delivers a heat map. This is a very abstracted version of it, where it delivers a heat map of important and maybe less important parts of the image that lead to a certain outcome. So we have different methods. We have different categories of methods. We have global and local methods, trying to explain an entire model or just one decision alone. We also have model agnostic or model specific, depending if you want to use an explainability method across different models that you trained, or if you want to do it specifically for one model. We also have ad hoc and post hoc and even anti-hoc methods, depending when we are trying to employ these methods. Is it during the training of the algorithm? Do we already then think of explainability? Or is it maybe an afterthought to say, oh, it'd be nice to have some meaningful explanations on it? And then the question regarding time series and medical time series, how are these methods applicable to that domain? Because some of the methods employ or assume that the features are independent of each other. And with the temporal aspect of time series, we cannot do that. So we also have to be careful which methods we can use. Here I have three examples, one after the other, of XAI in time series and how it can be employed. It's not important that you understand every single part, but the idea on this one is that we train our model and then we try to find primitives. So for instance, sequences in the time series where the data increases, where it decreases, or on the right side, we try to find the primitives of local minima and maxima, so peaks and valleys. And then we use these primitives to try and distinguish between the different classifications, and we build simple decision trees saying that if the data is increasing at time x and y, then we're most likely to go into that direction, and then we look at the decreases when they happen. So we're trying to extract from the complicated time series some kind of features that are more easily understandable to us. Some of my own work, what we've done is patient breath-wise classification algorithms, where we applied on the top attention layers, and on the bottom we use Grad-CAM, which is actually for images, but you can look at the time series as a 1D image and then still apply Grad-CAM to provide heat maps of the areas where the image is most important, or where the part of the image is most important for the outcome. Now, we also went a step further, and we tried to ask clinicians, but also the developers, and ask them, is this helpful to you? So not just develop something, but actually ask, is this something meaningful? And providing information doesn't necessarily mean that you're going to clarify something, because additional information can, again, open up further questions. As it is the case for the upper one, with the attention weights, we were always asked, what are these attention weights? How can I interpret them? What is the meaning behind them? And that's something that we need to think of when we're developing AI methods, that maybe something is very intuitive for us, but it might not be for the users. But before we go to the applying explainable AI, there's also a very nice example on its uses during development. So here in the paper, multiple classifiers were developed to distinguish different CT scans, and they employed multiple XAI methods here on the top row, giving heat maps on which parts of the CT scan the classifier focused most for a decision. They used this as a mask on the actual CT scan to compare multiple classifiers. Here I have only two, and compare how they focus on the image. Now on the right side, we see the focus is pretty widespread. It's not on one single space. But on the left side, we can see that the main focus on every type of XAI is mostly on the top left corner. And that is because this classifier was shown to be biased to artifacts. The CT scan had the small letter D, which distinguished between more serious cases and less serious cases in CT scans due to some internal coding. And this is how they discovered that the classifier was basically not good. Even though typical evaluation metrics such as F1 score, accuracy, and so on was for both of them very good. So XAI gives us a tool that we can try and use and distinguish during the development part if a model is actually useful or not, and if it's going to be generalizable maybe in other hospitals. So they concluded that very small increases in validation accuracy can correspond to drastic changes in concepts learned by the network. And this is something that we need to keep in mind. Directly moving on to general pros and cons of explainable AI. We've seen how it can be used during development. And in general, it does provide insights. Depending on the application, they are more or less helpful. But it has been shown that it can increase patient compliance and improve patient autonomy, because you don't just have something like yes or no, but you have an explanation with it. So the patient feels more involved and is more willing to comply. It can also be useful during development, as we've seen before, but it does have also some cons. And the first one is called the automation bias, which means you get a CT scan and says pneumothorax yes. Then the first thing you might do is think why yes, and look at it. Now with explainable AI, you get a CT scan saying pneumothorax yes, but you also get an explanation. You read the explanation, you say, ah yeah, it's okay. And you do this multiple times, and you start to not really thoroughly read the explanations anymore. And this has been proven to happen, this kind of automation bias, that the explanation, even though they were sometimes wrong, were just accepted due to the continuous use and acceptance of these. Also, explainable AI, even though useful during development, we shouldn't, again, trust it too much, because there are possibilities to manipulate or attack the images or time series, which result in a different classification of them, so maybe into a false negative. But the explainability method is not showing up these kind of manipulations. Also, some methods you can use another AI model, so it's basically stacking a black box upon another black box to explain the first black box. So I don't know if that's really the best way to go. And it's also a little bit controversial. Some of the methods that say they are going to explain the method or the model in a working are not actually based on any kind of causality for the final reason making. And what I mentioned in the beginning with the liability, explainable AI can also affect this. So does explainable AI, if we offer an explanation, does this change liability towards the healthcare professional just because they now have an explanation? Or does it reside with the businesses and the developers behind it? So this is also an ongoing debate regarding explainable AI and how it can affect the liability. So there are a lot of to-dos in XAI. To start with, in the European AI Act, what is sufficiently transparent? Inherently, explainability is something subjective, something that each of us will perceive differently. So also evaluating AI methods, I think, should go further than just developing the methods and seeing, is it meaningful, it looks okay, but it should go on to comprehend multiple stakeholders and actually test if the acceptability, interpretability is what we assume of these methods. And there's relatively little research for these time series data specifically, also because they haven't been as available as data, image data. So if you're interested in a different research field, there's a lot to do. And finally, I would like to give you some food for thought with paracetamol, which is a widely used drug with an incompletely understood mechanism. So basically, you could say it's a black box, but we accept it. It was put through a trial, and I guess myself and maybe you also already profited from the benefits of paracetamol. So this raises the questions, when do the positive outcomes outweigh our lack of understanding? When will we satisfied that AI has a positive enough impact to not question its understanding? And is this a double standard for AI, comparing that it's not applicable always to drugs? Thank you.
Thank you, Camila, for this great talk. Very interesting questions. Yeah, how do you, yeah, for me it's quite complex, but how do you rule out this kind of errors, and how do you find, because it's so complex, how can you rule that out?
So you mean the errors like with the CT scans and the letters, or?
No, like if the algorithm or whatever, like the AI does,
yeah,
if there's some
mistake,
or if like maybe the data is not clear, like that was like
yeah. It's difficult. There are different methods for it. I guess the first thing is to think that there could be a bias in the data, for instance, because sometimes people just ignore it. So being aware of that is the first step, and then using appropriate methods to counteract it. And with explainability, as I've shown, you could look in which areas of the time series or an image the focus is. And if you look at that multiple times, and of course with the necessary medical background, you can detect a systematic bias or systematic wrong detection. And then you, depending on the algorithm, you can steer it in a different way. Yeah.
But here I think one of the important questions which you raised, explainable for whom?
Yeah.
Because it's completely different what computational researchers see as explainable, and then turns out that for the doctors it's completely meaningless information.
Yeah.
Right? It needs to be somehow translated, so they're different, indeed, they're very different ways of. But I also believe that we need to add to stakeholders, researchers who are developing those algorithms, because if you really look at the explainable AI, it can also help you to understand that your algorithm is doing something sensible and not, detecting some artifact in place of the actual, movement. And this is really missing out in the curriculum, I believe.
Yeah.
And was that your cat and your dog? That's my other
Yes.
Because it was the same.
It wasn't, yeah, I did it on purpose. I did it on purpose.
I thought you were going to show a muffin,
Very cute.
So yeah, I think maybe this was also what I didn't understand about this example you showed with the individual breaths, because you showed a classification of where the algorithm puts the attention, but in the end, this doesn't seem like an explanation to me.
Yeah. So that's the correct question to ask. For instance, if someone is lacking the domain knowledge, it might not be an explanation. But if you go to into therapy, so you do get some additional explanations while you're asking questions. So of course you can, I don't know, create different grades of explainability. So maybe for people targeted for people with less domain knowledge to offer more explanation. But for the clinicians that we tested this with, they said that the areas the AI focused on was meaningful in cases where there was a complication. In the cases where the complication was missing, there was no area that was meaningful because everything was okay. So in that case, the attention was like everywhere and it didn't make any sense. So it depends on domain knowledge, but it also depends on the specific cases if it makes sense or not.
But could you, for example, if you say, I'm not quite sure if that detects what I wanted to detect, you could change like a variable and see what happens then if that still goes with your hypothesis.
Yes, this is what Lime and SHAP do.
Yeah, that's cool.
That's the reason behind them.
You need to create the data to test your algorithms on before.
Yeah.
Just like no one does it because they're test-oriented development is a new thing. It's very theoretical.
Into the fame.
Yeah.
Which AI model did you use?
So we tried, to be honest, I'm kind of moving away from Explainable AI because I'm moving a step further and asking if we actually have to employ complicated AI methods in every case. So that's my field of research now, where I try to compare simple algorithms with more complicated ones. Because in German it's like mit Kanonen auf Spatzen schießen, so trying to shoot down sparrows with cannons, where we usually even don't have the data enough for it. So what we did there were attention layers, Grad-CAM, and we also tried Lime and SHAP in the past. So the methods that I tried to show. So basically changing input features to see the outcome, how that changes, to say which feature is most important. And also with Grad-CAM, with that heat map, to see which parts of a signal were more relevant for the outcome. But they are way more complex method than this.
Basically, it's a heat maps. You get it based on the measurement or data.
Yeah.
And which dataset you have your own dataset?
We have our own dataset. We are collecting our data on the University Hospital in Aachen, where we have a setup where we can collect the entire high-resolution data from neonatal patients.
And you stay the bias method.
I'm sorry?
The bias method. For
Yeah.
What's about Monte Carlo methods in the classification?
Yeah.
It's nice.
Yeah, you could also try that, definitely. Yeah. You have to focus at some point on some kind of method, but that is something that one could try. Yeah.
Going to simpler methods instead of explainable.
Yeah, that's what I mean. So I'm going to the anti-hoc explainability. So before even complicating the algorithms.
Yeah, maybe into this topic, is it possible to use explainable AI to end up with a simpler model that might be better than the original neural network that was investigated?
So I'm not sure if this has been globally done for a model, but this is something that you can do for a local decision, where you have one decision, okay, this is a cat, this is a dog, and you can approximate for this specific decision a very simple model. So it's called a glass-through model, I think it's called, because it represents a more complicated model in a very simple way. This is exactly what is done, but I'm not sure if you can do it globally. You can do it locally, or maybe for a group of classifications.
But we definitely can go to the feature importance and then reduction.
Feature reduction, and then to use your inputs.
Or you can start with a simple one.
And see if that is not good enough too. Yes.
It's nice to see that, for example, all this stuff is not important. That you figure that out with the big model.
Then take it out.
But big models also make sense to drop everything which you have no idea about just in and then see what makes sense.
That's not proper science.
You know, like the last slide.
Yeah.
But which also brings us to the point where in silico trials, should become a bit more acceptable, because the reality is that we don't really understand how black box is our own physiological body, and that in silico, alternative.
Yeah, true.
Yeah. Thank you so much.
Thank you too.